More correlation. Why more correlation? We've already started discussing correlation. What more concepts are there to discuss? In today's session, we'll cover some exceptional cases that are commonly encountered in research studies and how they affect the applicability of the correlation coefficient to those data. We'll also look at the SD line and how that is related to the correlation line and the regression line, rather. And we'll finally discuss ecological correlations and some of the trouble associated with ecological correlations, which are used frequently in health and social research. Finally, we'll cover the relationship between correlation and causation. Before we get started, let's review a couple of key concepts from correlation part 1. Scatter plots are the first step when doing a correlation or a regression. Why do a scatter plot? Because you need to look for a linear association between your variables, and a scatter plot is a very helpful, quick way to assess the linearity of the association. It also gives us insight into the presence of some exceptional cases that we'll discuss today. The scatter diagram is summarized by 5 essential statistics, and we'll use these statistics throughout our treatment of correlation and regression, so they will continue to be important both for correlation and for our future work in regression and modeling. These are the average of the x values, the average of the y values, and the standard deviation of the x values and standard deviation of the y values. And this is a standard set. You very commonly, when dealing with interval variables, the average of the variable and the standard deviation of the variable are statistics that are commonly used in the more complex measures of association and relationships, so you'll get used to seeing those. The correlation coefficient is our final essential statistic to describe a scatter diagram. We could see on a scatter plot a positive association where 2 variables go up together or go up or down together. Both x and y go in the same direction. With a negative association, we see variables going in opposite directions. As x goes up, y goes down. The final thing we get is an idea of the strength, but you get a better idea of the strength from the correlation coefficient. You can see the strength in how closely packed the points are around the line. It's important to remember that the correlation coefficient ranges from -1 to +1. So if you're presented with a correlation of 2, you know you've done something wrong or it's a trick, because there's never a correlation of 2. They're always between -1 and +1. And it's important to take note of these ranges because there's a lot of our statistics have a predetermined range like this. And when you can keep that in mind, it helps you to assess easily whether or not there's some problem in the calculations or in your conception of what's going on. The standard deviation line goes through the point of averages. When r is positive, the slope of the line is the standard deviation of y over the standard deviation of x. When it's negative, the slope is the same, but it's a negative value. And to calculate the correlation coefficient, you can convert each variable to standard units and then take the average product. when we look at some features of the correlation coefficient, it's important to remember that it's a pure number. The correlation uses standard units and it's unaffected by changes of scale. And standard units should sound familiar to you because we were introduced to standard units in our first discussion of the probability distribution and the z-scale. So the z-scale are standard units, and that's the easiest way to think about standard units, is to go back to your thinking on the z-scale and how you can turn any raw score into a z-score, given that your raw score comes from a variable that's normally distributed. In this problem below, I want to highlight a quick point, which is that if you switch the columns, x and y, the correlation is the same because it doesn't matter with correlation which variable goes in the x or the y location vis-a-vis the actual correlation coefficient. Thus, you'll get the same correlation coefficient number whether you put, the predictor in the x or the predictor in the y variable. However, there is a strong convention to put the predictor in the x variable and the outcome in the y variable. You could also think about this as the independent variable in the x, the predictor, and the dependent variable in the y. And the reason that there's that strong trend is that when we move into regression, then that's standard, and correlation is intimately tied with regression. So it's good to generally structure your analyses that way if possible. Sometimes it's not possible to know which variable of a correlation would be the predictor, but oftentimes we can. Another issue is related to changing standard deviations. So the appearance of a scatter diagram depends on the standard deviation. So looking at this figure, you can see at the figure on the left, the points are packed more closely in a smaller range of scores on both the x variable and on the y variable. However, these two scatter diagrams have the same correlation coefficient. It's 0.7, and you can account for the difference in the spread by using the standard deviation. This is why when you're reporting statistics, which we're going to practice increasingly in the next couple units, there are certain sets of numbers that are generally reported, and among them are your standard deviation. And here's why. Because the graph isn't always available, but it's important to communicate to your audience that what the spread of the scores is like. The correlation doesn't capture everything. And as you see here, as r gets close to 1, the distance of a typical point above or below the standard deviation line becomes a small fraction of the vertical standard deviation line. So the closer r is to 1, the smaller the fraction, the vertical SD. This factors into the, again, topics that we'll revisit when we dive into things in more detail in regression. it's also important to take note of these exceptional cases. So there are actually more exceptional cases than these two, but these two are just cases that are commonly encountered in social and health research, and it's important to know how to deal with them if you encounter them. One of those is the outlier. You can see this illustrated in figure A. In this figure, there's a clear line through the points, except for the point that lies at 6,1. That point is a substantial outlier, and when you do a correlation in the presence of an outlier, so with that outlier in your data set, it's going to make the correlation coefficient not as accurate, and it's misleading. So you would either, in this situation, it would depend on the reason for the outlier. Oftentimes researchers will drop an outlier from the data set and then explain in their write-up why the outlier was excluded from the data. They'll say there was an outlier at a specific point, it's given and explained in terms of the actual variables, not just that the point was at 6,1, but and the reason for justifying the outlier would be given. With the outlier in the data set, the correlation, you really can't use it. If you exclude the outlier, you can use the correlation, with an asterisk, with the asterisk being that you give some explanation of what happened to the outlier and how it was theoretically acceptable to exclude them. In figure B, we can see a nonlinear association, and this particular nonlinear association is called a curvilinear association because instead of being a line, it's a curvy line. And when you have a nonlinear association, you can't use R at all. There really is no scenario for effectively using R to describe this entire data set. Sometimes researchers do, when they have theoretically justifiable reasons, they might say, well, hey, you can get to this point. You can see in the middle of the figure B here, there's a point where the values level off and then start to go down. So they might say, well, let's just look at the correlation for this first interval, create some new variables that just look at that interval, but that's not really a very statistically sound treatment. So you do sometimes see that happening. It's true that in the research literature, you don't always see things being done perfectly. Part of what you'll hopefully take away from this class is the ability to be a critical reviewer of such research, so that you would be able to, when reading, a write-up like that describing that sort of treatment of a curvilinear association, say, oh, I know that's not right. You might say then, well, I don't know exactly the right way to treat a curvilinear association because we really can't cover that in this class. We just don't have time. But trust me, there are methods for doing it more reliably. And if you were personally confronted with computing or dealing with this sort of analysis, you could find the methods to do that relatively easily, hopefully with the skills that you'll have by the end of this class, through lab and other ways. We'll go through resources for what's next if you were addressing more complex situations, but most of the time you won't see a nonlinear association. Outliers, on the other hand, they're pretty common. If we look at these diagrams, let's just quickly go through this plot. You can see that we want to assess, based on the scatter diagram, whether or not we can use R. And it's important to keep in mind that You can use R anytime you have variables that are both at an interval level and are normally distributed. Of course, in order for a variable to be normally distributed, it has to already be an interval variable or have an interval level of measurement or a ratio. So when we look at the first problem here, you can see that it could easily be summarized but using R, because the points are all together in a cloud. There's no outliers, and there's a generally linear association. Although you shouldn't prejudge the association based on the scatter plot, you really need to look at the R value at minimum to get a good feel for how strong the relationship is. But what we're really looking for here are the presence of things that would nullify our use of R, like outliers or a nonlinear association. In figure 2, you can see that there's an outlier in the bottom right corner. So we really can't use R on the data set as it is. In figure 3, this is a different type of nonlinear association. And again, it would be best to avoid use of R on this data set. Let's discuss this problem too before we move on. Here we have a class of 15 students that happens to include 5 basketball players. Now, logic dictates that the basketball players are probably taller than average. This is something I think it's fair to say most of us already know about basketball players. So with that in mind, assess whether the relationship between heights and weights for this class should be summarized using R. What are you? So think about this for a minute. The key thing to think about here is is your sample generally laid out in a normal distribution? Well, it's probably not laid out in a normal distribution if 1/3 of your sample is from a different population. That population being basketball players, who are on average taller than non-basketball players. So because we have a sample here that is unlikely to be normally distributed and also contains two participants from 2 populations, which will unpack this idea of a population more in the very near future. So we really can't use R in this case. It just, again, the variables aren't normally distributed. And so we'd have to consider a different statistic here. But this is a common issue, and it's something that's important to keep in mind, that ultimately that sort of information is something that would weigh heavily in guiding your choice of analysis. Moving on to ecological correlations. So an ecological correlation is based on a rate or an average. A rate is, anything that's a quantity per unit. So usually, we're very familiar with things like infant mortality rates, mortality rates generally, prevalence of illnesses. Prevalence is a rate that so especially in health research, but also all over in social research, rates are used. They are convenient for a lot of reasons, But when rates are used in correlation, then it's called an ecological correlation, and it's problematic because ecological correlations tend to overstate the association strength, and that's troubling on a couple levels. Of course, we want our data to be as appropriately stated as possible, to not under or overstate a relationship. But it's especially problematic when a relationship is overstated, because then you're, because of the publication bias, where results that show a difference or show a relationship are much more likely to get published, it will tend to put the results out into the academic research canon, but that may not be appropriate. And it certainly is appropriate, and I would argue incredibly important, to publish null results, so results that don't find an association between variables. It just is not the reality in publishing in our current state of academia. So ecological correlations are troubling, and you'll encounter them a lot in research that you read. So keep that in mind when you're reading research where you see a correlation that includes a rate or an average, and then you should then take their data with a grain of salt, so to speak. We're going to look at an example in a minute, but let's first just briefly go over this issue of association and causation. These are very different things, and this is incredibly important to remember, that correlation is not causation. Causation can only be assessed when an experiment has been conducted. Correlation and association is very commonly used to describe observational data and survey data. And while it is a very useful tool, and for a lot of issues, it's really only reasonable to get survey data or observational data. We can't always do an experiment where we randomly assign people to different groups, but it's important to remember, because you've got to be careful with the language that you use when presenting results. So correlation can only be related. It can never, a change in X can never, the predictor variable can never be found to cause the outcome variable. We can only find them to be associated or not. And it is true that calculations cannot protect you from errors in logic. What do I mean by this? Well, just because you can find a calculation doesn't mean that it's an appropriate calculation for that research methodology or for that variable. So for example, you could have data where that's coded men and women. Women are 1, men are 2. And you could find a mean of those, but the mean would be not meaningful. You cannot, because gender or sex is a nominal variable. There's never a situation where the average is an appropriate, or let's say valid, measure for a nominal variable. But a statistical program will do whatever you ask it to do. So you have to keep in mind when you're asking it to do things, that you're asking it to do things that make sense for the variables you're studying. This might seem obvious, but it's trickier than you might think. This often causes students a lot of trouble. Let's think a little more about the correlation. Why does correlation not equal causation? Because in correlation, we're just looking at the association between two variables. We're not accounting for confounding variables, and because we don't have an experimental method, we haven't been able to randomly assign participants to groups that are matched based on variables that we expect to be potential confounders. Now, there do exist complex survey designs that do a good job of addressing this problem by adopting what we call a stratified design or a probabilistic sampling. And we'll talk a little bit more about these more complex types of sampling later on in the course. But and as an example of some studies that do use those methods, the GSS survey that we look at in lab, the big population surveys do tend to use stratified sampling or some kind of probabilistic sampling that helps to account for potential confounders, but it still can't fully account for them. So we really can't, again, we can't infer causation from correlation, primarily because of confounders. Let's look at this scatter plot and regression line and think about what's happening here. On the x-axis, we've got fresh lemons imported to USA from Mexico. And you can see on the y-axis the total highway fatality rate. And the clear negative correlation here as more and more fresh lemons are imported to the USA from Mexico, there's a significant drop in the total highway fatality rate. So do importing lemons, cause a decrease in highway fatalities? Well, probably not. You should all be saying, well, no. And that's also apparent because of the topic here. Well, why not? What's the third variable that's going on behind the scenes that accounts for and is associated with both of these? There's a hint on the slide already. Hopefully, you're thinking about time, because you can see here, looking at the diagram, that there's also a clear relationship between the year and both highway fatality rate and fresh lemon imports. So over time, since 1996, more and more fresh lemons have been imported to the US from Mexico. On that same time span, we see a decrease in US highway fatality rates. And I would predict that there's a specific third variable that accounts for this decrease in highway fatality rates, that third variable being the seatbelt law. So it didn't used to be the law that you had to wear a seatbelt. It wasn't an enforceable law at any rate. And then the law was changed so that it was possible to get a ticket for not wearing a seatbelt. And gradually, people started wearing their seatbelts more and more. Well, wearing a seatbelt is known to reduce the risk of a highway fatality. And so that's a third variable we see that accounts for this association. This topic is one you should definitely want to feel comfortable with. I can promise you it'll be assessed on this exam and the final. It's a really important point. Oh, before we move on, is this an ecological correlation? Yes, it is, because we have a rate, the highway fatality rate. So we know this may be an overstated correlation, but as we know, it's sort of a nonsensical correlation anyway. That's just to help illustrate the correlation and causation. I'll do one more. correlation and causation relationship. It's my favorite one because ice cream and consumption of ice cream, increased consumption of ice cream, is associated with an increased rate of homicides. So, does ice cream cause people to commit homicide? Not likely, no. But there's a third variable here that accounts for both of them. So, as the temperature goes up, so does consumption of ice cream. And likewise, as the temperature increases, so does the homicide rate. Heat makes people more violent. I already feel that way. It's already too hot here for me. So that's what accounts for the ice cream homicide rate correlation, which is kind of a famous one. And this is just another example of an ecological correlation. So you might see this overstated. Let's practice identifying one more third variable before we move on, because like I said, this is really important. Studies find a negative correlation between hours spent watching television and scores on reading tests. Does this mean watching television makes people less able to read? What do you think? Probably not. You can see the pattern here, but beyond that, why not? What's the third variable here that is associated with both hours spent watching television and scores on reading tests? Thank you, Tori. That is exactly the third variable I have in mind. When people spend more hours watching television, they have fewer hours available to actually read books. So that's that's just obvious. And in terms of there's only a limited number of hours in a day. So if you take up 10 hours in a day watching television, how many hours could you be spending reading? And unfortunately, people do spend a lot of time watching television. Now, the other thing is that we know more time spent reading is associated with scores on reading tests. Again, this makes perfect sense. So this relationship functions through a third variable, hours spent reading.